what's inside the electron?
I have to ask my friend, professor of physics. He might know the answer.
Okay.
Yeah, we're at the St. John Fisher College, the chemistry and physics department, and Dr. Munawar Karim, professor of physics, and he had a nice publication about the structure of electrons. So we'll be talking about the structure of the electron. How important is the electron in the universe? It's one of the elementary particles.
Yes. There are only two stable elementary particles, electrons and protons. Every other particle is unstable, and there are hundreds of them. So these are two particles that if you understand the physics of these two particles, you can understand the physics of every other. In that sense, a very clean example to study because you don't have any interfering effects.
Mm-hmm. What is the electron made of?
It's pure field, electromagnetic field. There's nothing there. It's just pure. There's no solid, nothing, no structure.
But the field somehow is localized into a particle.
Yeah, that's right.
How that is possible?
That's the question you might ask is why is the electron stable?
Yes.
So the electron is repelling from itself all the time. So it should fall apart. But it doesn't. So this is the central question. Why does it not fall apart? So the question is what holds it together, right? And people have, 1895 to now, 120 years, people have tried to explain this and they have not succeeded. Many people who study physics, their natural inclination is to look to mathematics to find a solution. So when you calculate this, why it is being held together, you'll find, if you do this calculation, you'll find you get an infinity in your equation. And so all these 100 years, people have tried to avoid this infinity, find a workaround, find some residue, this. But nature is telling you this infinity is real. It's real. You cannot avoid it.
Mm-hmm.
So once you accept that this infinity is real, you ask yourself, why is it infinite? You will get a pressure, Alex, you won't believe. It is 10 trillion atmospheres.
Huge pressure.
It's pushing it outward. 10 trillion atmospheres from the earth is pushing it outward. So here's a question, why doesn't it explode? This is the puzzle. This huge pressure is pushing outward. Something is pushing it back in at the same force.
And the forces equalize each other.
Something is making it, providing a compensating. So this was the puzzle. So now you ask why. So now you have to start thinking about Einstein's equation of gravitation, the two sides. The right side is matter. So matter tells space-time how to curve. And space-time tells matter how to move. So this is the equation. Right?
Mm-hmm.
So you think about it now. Here is matter telling space-time how to curve. It is curving. You can see here, this is how it's curving. You can see how the metric is no longer flat. Just like the metric is pushing the electron to contain it.
Mm-hmm.
So matter is telling space how to curve, and space-time is telling matter how to move.
Mm-hmm.
So space-time is what is pushing the electron in and containing it.
And that's the gravitational.
That's right. So now you do this whole lot of calculation now, and then you find what should be the energy density of the electron, that's radius, for it to match its own external gravitational field. And you will get the electron radius. And you find 10 to the power minus 37 meters.
Oh, and now
you know.
Wow.
Now you know.
Yeah.
So, but in the process, as I was saying, you find this unexpected results that you find, first of all, to stabilize the electron, you have to bring in the gravitational field. Otherwise, there's no way it can be stabilized. So now you have a field theory with gravitational built into it, not separately, it's into it. This is the first time, okay. So now you understand that all of elementary particle physics is, the theory does not have any gravitation in it at all, no gravity. And if you ask them, they'll say, oh, at the beginning of the universe, when all the fields were together, but somehow gravity split off and everything else kept going, right? But now you can see it's not so. It was always there. It never split apart. It was always there. Even today, it is still there. So you have to now rebuild elementary particle physics with gravity built in from the get-go. It's all from textbook physics, Alex. There's no assumption, no approximation, nothing. Your textbook physics.
And this technique, this method, can it be applied to all other particles?
Yes, that's right. And now you think about it, you read about like the Higgs boson or quarks and so on. They are never seen outside. The reason is now that this field, right, it has elastic properties. Yes. So it can set up standing waves. Standing waves. And these standing waves exist for a while, then it collapses. So these particles, like the Higgs boson, they are standing waves in this field, W boson, the standing waves. You can never see them outside. No, because the standing wave.
Okay, so that's just not a real particle
No,
then.
it's not. It's an excitation. Yeah, it's like a violin string. It's vibrating. You cannot see the vibration outside
But
the
that,
string.
it means you can create hundreds, thousands of those particles.
That's why there are hundreds of particles. Muons, protons, gluons, Higgs boson, W boson, Z boson, and on and on. It's like a periodic table of particles. Yes.
So the real particles are only two, the proton and the electron, and that's what the matter is made of.
That's right, yeah. That's right, yeah. But that you find that this energy where all these things come together, right, all the fields, it depends only on two fundamental constants, the electric charge and the gravitational constant. Does not depend on the speed of light, does not depend on Planck's constant. This is amazing, and it's coming out automatically. So I said to them, this is what's telling you that the gravitational field is not quantized, it's a continuum. That now you're back in the 19th century, it's not quantized, it's before quantum mechanics.
It can be still quantized
Afterwards.
outside of the electron, but inside
Afterwards.
it is a classic.
Afterwards, when it is evolving at a much lower energy, it becomes quantized. It's true, but it's at extremely high energies, it's not quantized. Because it is so elementary. Well, people suspect something is wrong in the argument, but it is so elementary. You can follow the argument from like first freshman physics course, right?
Yes.
There's nothing complicated there, but you have to, in your mind, you have to open your mind.
Well, okay, thank you. I'll
Well, thank
try
you.
again.